Hi everyone, this is the video for class 25 of PH 125, and today we're going to continue talking about simple harmonic motion. In this video, we're specifically going to focus on the oscillation of a mass on a spring. We'll do a brief introduction to the motion of a pendulum, and we'll be continuing that discussion in the next lecture video. Okay, so just a quick summary of the things we learned last class about simple harmonic motion. Remember, we said that the period of oscillation of the motion is t. So this is the amount of time it takes to complete one full cycle of the periodic motion. Then we said that the frequency of oscillation is just 1 over the period. So in other words, it's the number of oscillations per second. Okay, we also defined this quantity called the angular frequency. It's related to the angular speed when we think about the relationship between simple harmonic motion and a point mass in uniform circular motion. But in general, angular frequency is just 2 pi times f, or in other words, it would be 2 pi divided by the period t. Okay, and so then we learned that if we think about simple harmonic motion, for example, a mass on a spring, where we have an initial displacement of a, then our position as a function of time is well represented by a cosine function. Specifically, x of t is equal to a, that's the amplitude of the motion, times cosine of omega t. Omega, again, is that angular frequency. Okay, and then what we learned is that the velocity as a function of time will be related. It specifically is going to be equal to minus a omega times sine of omega t. And in thinking about these problems where you're asked to relate the position versus time and velocity versus time functions for a simple harmonic motion type of experiment, it's probably easiest to just remember that the velocity as a function of time is the slope of the position versus time curve. That will help you in deciding what your velocity versus time curve should look like. Okay, and then acceleration as a function of time we discovered was equal to minus a omega squared times cosine omega t. And this is going to be the slope of the velocity versus time curve. Okay, so let's look at some examples here. So our position as a function of time, it starts at some maximum amplitude a. And so the cosine function, cosine of 0 is equal to 1, right? And so when we look at this position as a function of time function, we would get 1 times a, and so in other words, we want to have an amplitude of a at time t equals 0. Okay, and then the position as a function of time will oscillate back and forth between plus that amplitude and minus that amplitude. So it'll be at minus that amplitude at the lowest points. Okay, and it oscillates back and forth with one full period. So I would say that the amount of time for one full period would be the time to right here, right? So this amount of time, that would be one full period, because you can see we start at a positive value and it's curving downwards, right? And then when we get back to this time over here that I've marked, then we also are going to have a positive amplitude, a positive displacement, and we're going to have that curving downwards. So you can see the shape starts to repeat itself after that marked period. Okay, and so then we see here that the velocity as a function of time, if x is equal to a maximum, so if x is equal to a, or if x is equal to a minimum, so in other words minus a, you're always going to have velocity equal to 0. So you'll notice every time that x is a maximum, your velocity is 0. Okay, so this happens every time that x reaches either a or minus a. Okay, so that's a good way to figure out how you can draw your velocity if you have the position or vice versa. The other thing to think about is the fact that velocity is the slope of the position versus time curve. And so here you'll notice that the slope of the x curve right at the beginning, it's negative. And so that's why the velocity goes negative to begin with. If you look at the slope over here, the slope right here is going to be positive, and so that's why you end up with positive velocities beyond that point. And right at the maxima or minima, that's where you have slope equal to 0, and that's why your velocity curve will always cross through 0 right at those times. Okay, so now let's look at position and acceleration. So position and acceleration, they should always be like, one will look like it's flipped over the time axis compared to the other. So they should both either be cosine functions or sine functions, and they're related by their amplitude. So the amplitude of the acceleration is going to be a times omega squared, whereas the amplitude of the position is just a. And I forgot to mention the amplitude of the velocity versus time curve is always going to be a times omega. And the way that I found those different amplitudes is just by thinking about what amplitude would I get, what's the maximum magnitude I could get, and that corresponds to the times when cosine and sine are both equal to 1. So those are the maximum values. So the maximum value that cosine can take, the maximum value that sine can take, it's always just 1. It oscillates between -1 and 1 all the time. And so then whatever is out in front of each of those different functions, the magnitude of whatever is out in front of each of those different functions tells you about the maximum value of those functions that you could get. So x max is going to be a, v max is going to be a omega, and a max is going to be big A omega squared. Okay. And if, for example, your position is shifted by 90 degrees, then that would be like the same thing as it being a sine function. And so you can actually shift either cosine or sine by 90 degrees, and you end up with the opposite function. Okay. Let's do a quick example here in thinking about simple harmonic motion. So an object in simple harmonic motion has a maximum speed of 4.3 meters per second and a maximum acceleration of 0.65 meters per second squared. And first question we're asked is to find the amplitude of this motion. So first thing I would remember, I would look over at this blue box, the equations in the blue box here, and we can see that, remember, the stuff out in front of the sine or the cosine, the magnitude of the stuff out in front of the cosine or sine, so in other words, the stuff that gets multiplied by sine or cosine, that tells you about the max values. So just looking at that box, I see that V max is going to be equal to A times omega. And we should see then also that little a max, the maximum acceleration, is going to be a times omega squared. Okay, and so that means that I have two equations that relate to unknowns. So we have two unknowns, one is the amplitude and one is omega. So we have two equations and we have two unknowns, so that's great. So we can go ahead and, plug one in for the other and solve for one of our unknowns. So here I want to solve for A, which means I want to get rid of omega in one of my two equations. So let's go ahead and rearrange this equation for omega. I would get omega is equal to V max divided by A. Okay, and then what I'm going to do is I'm just going to plug it in for omega in this equation. And so I get A max is equal to A times omega squared, where omega is V max divided by A. Okay, so when we square it, remember we have to square both terms. And so that gives me A times V max squared divided by A squared. Okay, so one of my A's will cancel, and I'm left with V max squared divided by A. And so then what I can do is I can just solve for capital A. That's the thing I'm looking for. That's the amplitude of the oscillation. And so when I solve for capital A, I just get V max squared divided by A max. And now we're ready to plug in some numbers. So V max was 4.3 meters per second. We want to square it, and then we divide by A max, which was 0.65 meters per second squared. And so when I plugged those numbers in myself, I ended up getting 28 meters. So that's a pretty big amplitude. Okay, so that's the amplitude of our oscillation. So in other words, if we were looking at a position versus time curve, it would look something like this. It's oscillating around x equals 0, and this maximum height would be that A. So that maximum height above x equals 0 would be 28 meters. Okay, next we want to find the period of this motion. Well, that's actually fairly straightforward now, even though it might seem like we don't have nearly enough information. So what we can do is we can really solve for omega, and remember that omega is equal to 2 pi divided by the period. Over here, we found that omega was equal to V max divided by A. So let's use that equation. It's equal to V max divided by our amplitude. V max is 4.3 meters. And then we want to divide by A, which we just found was 28 meters. Sorry, meters per second up here for the velocity. Okay, and then we want to divide by 28 meters. Okay, and so when I calculated that out, I got omega is equal to 0.151, and this would be in radians per second. And so then I have omega, and so it's pretty straightforward to calculate the period. Rearranging this equation up top, that omega is equal to 2 pi over t, I would get t is equal to 2 pi divided by omega. Okay, and so then that's just going to be 2 pi divided by 0.151 radians per second. All right, and so then I end up with seconds in the numerator, which is great. That's what I want for the period. And when I calculated that out, I got 42 seconds. So that'll be our period here. Okay. And so now I want to take a closer look at a specific example of simple harmonic motion. So remember when I first introduced simple harmonic motion, I said that we're going to talk about two different types, a mass on a spring and then a pendulum. So we're going to start with the mass on a spring, and here I want to think about a mass that has been stretched from its equilibrium position to some maximum amplitude A here. So you can see I have an x-coordinate system at the bottom of the slide. The equilibrium position is where x equals 0, and initially I have my spring stretched by this amount A from its equilibrium position. All right, so that's my first thing, and so if I were to go ahead and let go of the mass, right before I let it go, it would have a velocity of 0, and its acceleration would be negative because we know that the spring force always pulls in the opposite direction compared to the displacement. So here my displacement is in the positive direction. That's the displacement from equilibrium. So that would be our x here, which is going to be A. And so then the force exerted by the spring on the block is going to be in the opposite direction. It's going to be pointing to the left. And so what that means is that the force exerted is to the left, and so then the acceleration of the block will also be to the left. And so I'm going to end up with an acceleration that's less than 0 in this case. So I have my summary right over here. We have x equals A, v equals 0, and acceleration is less than 0. Okay, then our block is going to move. Eventually it will move through its equilibrium position. So right when the block is at this x equals 0 location, that's our equilibrium position. Okay, and so then right as the block goes through that point, we know that F, again, the force exerted by the spring, is equal to minus kx. But right at that time, x is equal to 0, so our block is going through its equilibrium position. And so what that means is that there's no force exerted by the spring, and so right at that moment in time, there's no acceleration. So right at x equals 0, we get A equals 0, and our block is going to be moving to the left because it has been accelerated to the left from the previous step. Okay, so the velocity is negative, in other words. All right, and then our block, it keeps going. It passes that equilibrium position and it reaches some maximum compression. And it turns out the maximum compression is actually minus A. So now x is equal to minus A. That's its position when it's maximally compressed. And then when it's right at that position, it turns out that its velocity is going to be 0. So this is kind of like, remember when we did free fall and we threw a ball straight up in the air? Right when the ball changed direction, so right when it went from going upwards to turning around and coming back down, remember it had to stop just for a second right at the top of its trajectory so that its velocity could change directions. And that's exactly what happens here as well. So the block, it was going to the left, but after this maximal compression, it's going to be going to the right. And so this maximal compression, this is right at that moment in time when it's about to turn around, and so its velocity is 0 here. All right, and then we can think about the acceleration. Again, F spring is equal to minus kx. Here, x is minus A, so it's going to be to the left. That means my force is going to be pulling to the right. So it's always in the opposite direction. So since my force is positive, my acceleration is also positive here. Okay. Next up, our spring will go back to its equilibrium position. So it goes back through equilibrium, but this time it's moving from left to right. Before it was moving right to left. Okay, so now its velocity is going to be positive. Again, right at that equilibrium position, x equals 0, and so then our spring force is 0 as well, and so the acceleration is also 0 right there. Okay, lastly, the block will stretch itself back out to some maximum compression. Again, it's going to be plus A, just like the first time, just like where we started. And so then, once again, this is this moment in time when the block's velocity is going to be changing. It's going to be going from positive, switching to negative, and so right at that moment in time, the velocity has to be 0. It's right when that velocity is changing direction. Once again, our spring is stretched, which means that the acceleration is going to be in the negative direction. It's going to be pointing from right to left. Okay. And all of these different things are plotted on the right-hand side of our slide. So I have the different time points that we talked about are all marked by these vertical lines. And so you can really see what happens in terms of, x equals 0, the velocity is maximum and negative, and then the acceleration is 0. So that's right this second time point right here. Our third time point, we have the x position is at its negative maximum, right? So negative a. That's when we had velocity equal to 0. So our velocity versus time curve that goes through 0. And a is going to be at a positive maximum right there. We can keep going. Our block goes back through equilibrium. So that would be this third time point here, this third dashed line. And so then as it goes through equilibrium, x is 0. The velocity at this time point is going to be positive, and it's the maximum value of velocity that you can have. And right at that point in time, remember, since x is 0, our force and our acceleration also have to be 0 as well. All right, and then we want to look at our last time point here. So this is the last dashed line. This is when we return back to our starting position, right? So this is when x is equal to a. It's the maximum displacement from equilibrium. Right at that time point, remember the velocity has to be 0 because it's changing directions from positive to negative here. And our acceleration is going to be maximum, and it's also going to be negative. So the reason why it's maximum is because that's the maximum stretch, which means you get the maximum force, and so you have to have the maximum acceleration, magnitude of acceleration. All right, last comment here, the maximum position, the maximum velocity, and the maximum acceleration, of course, are all going to be related by these equations in the blue box at the top of the page. So remember, these all occur when cosine is equal to 1 or sine is equal to 1 or negative 1, as the case may be. So really the magnitude of the x, v, or a when cosine or sine is equal to 1 is what always gives you the maximum value of x, v, or a. So on the last slide, we really talked about one full period of oscillation for this mass on a horizontal spring. So it started at some maximum stretch from the equilibrium position, then it moved through equilibrium to some maximum compression. At the maximum compression, it turned around, moved back through the equilibrium position, back out to the maximum stretch. And so that's one full period of oscillation for this mass on a horizontal spring. And so now our question is, how long did all of that take? Or in other words, what's the period of oscillation for this mass on a spring? To find the period of oscillation of this mass on a horizontal spring, what we're going to do is actually find the angular frequency omega. Then omega is equal to 2 pi divided by the period. So once we have omega, it'll be straightforward to find the period. And the way that we can find omega is actually by relating the displacement of the mass on the spring from its equilibrium position at a particular time to the acceleration at that particular time. All right, and so then to relate those two quantities, what we want to do here is to draw a free body diagram for this mass on a spring. So here we're going to make the assumption that this spring at this particular time t has been displaced from its equilibrium position by an amount x, which is a function of t. And then we can think about drawing a free body diagram for this mass on a spring at this particular time t. So there are really three forces acting on this mass. We have the weight of the mass pulling downwards, and then because the mass is sitting on a horizontal surface, the normal force is going to act upwards. And then the third force acting on the mass on the spring is going to be the force exerted by the spring. Okay, and so that's really the force that we're interested in here. That force exerted by the spring, remember, it always tries to pull the mass and the spring back towards its equilibrium position. And so here, because at time t, our mass has been displaced to the right by some amount x of t, then the force exerted by the spring is going to be pulling that mass back towards its equilibrium position, which means that that force is going to be pulling it back to the left. Okay, and so now we can think about applying Newton's second law here. So Newton's second law tells us that the net force exerted on the mass on the spring in the x direction is equal to the mass on the spring times the net acceleration in the x direction. Here, that acceleration in the x direction, it's really going to depend on time. As we talked about on the previous slide, we know it's going to be changing as a function of time. And specifically, we know how it's going to change as a function of time. That's given by the equation up in the blue box in the right-hand corner. All right, then we can think about our other way that we talk about the net force acting in the x direction, which is by adding up all of the x components of the forces acting. Here, the normal force and the weight are both completely in the y direction. They have no x components. And so then the only force acting in the x direction is the force exerted by the spring. From Hooke's law, we know that the force exerted by the spring is equal to minus kx. Here, x is going to vary as a function of time as our spring and mass oscillate back and forth. And so then we're going to get x as a function of t. It is going to be given by our equation of motion for simple harmonic motion, x of t, up in the blue box in the right-hand corner. All right, and so now we have our desired relationship between acceleration and the displacement of this mass from its equilibrium position as functions of time. And what we can do is we're just going to plug in the relationships from simple harmonic motion that we have in the blue box up in the right-hand corner. We're going to plug those in for a of t and x of t here. All right, so that's what I did. I used a of t is equal to minus capital A, which is the displacement of the block, the maximum displacement of the block, the mass from its equilibrium position, times omega squared cosine of omega t. And then I plugged in for x, a cosine of omega t. All right, and so then we have a bunch of stuff that ends up canceling out here, which is nice. Cosine of omega t, we can divide both sides of the equation by cosine of omega t, and so that guy will cancel. We also have a minus sign on both sides, so those two will cancel, and we can divide by a. So a will cancel. All right, I think that's it. And so then let's just go ahead and rearrange that equation for k. And so what we end up with is k is equal to m times omega squared. All right, and so now we've achieved our second goal, which was to get a relationship for omega, because omega is the angular frequency, and that angular frequency is related to the period of oscillation. So remember, omega is equal to 2 pi divided by t, and so now all we have to do is rearrange and solve for t. Okay, so what I get here when I rearrange is that the period of oscillation for this horizontal mass on a spring is equal to 2 pi times the square root of m divided by k. So you can see it is going to depend on the mass of the block that's attached to the spring. It also depends on the spring constant k. So remember, that tells us about how stiff or stretchy the spring is. Okay, and so that was for a horizontal mass on a spring. What happens if we have a vertical spring? Well, if the spring is vertical, then we just have a shift in the equilibrium position of the spring when we add the mass. So let's see how that works here. So when the spring is in equilibrium, the net force acting on the mass that's hanging on the spring is going to be equal to the force of the spring pulling up on the mass minus the force of gravity downwards. So if we were to draw a free body diagram for our mass on the spring, it would be like F spring by spring upwards, and then the force of gravity, which is going to be mg downwards. Okay, so let's say that the new height of the mass, so the new height of the top of the spring, is equal to y naught. So we're just calling this new equilibrium position, we're calling it y naught. Okay, so then we know that the force exerted by the spring is really going to be equal to minus kx. So really here, y naught is going to be below y equals 0, that original equilibrium position. And so that would be like a negative displacement. So I would end up with, really my new position is going to be a distance y naught below the original equilibrium position when you don't have any mass on the spring. Okay, and so then our Newton's second law relationship will look like minus k times minus y naught. And so that's really just k times y naught minus the weight of the mass. Okay, so this is our net force. And when the object is in equilibrium, that means it can be at rest at that location. So that means the net force can be equal to 0, or in other words, K y naught minus mg can be equal to 0. And so then we can just go ahead and solve for y naught. So you can add mg to both sides and divide by k, and what you get is that y naught, our new equilibrium position below the old one, is going to be mg divided by k. Okay, so this is the distance below the equilibrium position of the spring when there's no mass hanging on the spring. All right, and then once you have figured out your new equilibrium position, basically you can treat it exactly the same as you treated your mass on a horizontal spring. So it will still exhibit simple harmonic motion with the same period, so 2 pi times the square root of m divided by k. It's going to oscillate around this new equilibrium position. So its new amplitude would be, some maximum and minimum distance below or above that equilibrium position, the new equilibrium position. All right, so with that in mind, let's do a little practice problem here. So which of these mass spring combinations will have the largest period of oscillation? Okay, so the key to this one is just remembering that period is equal to 2 pi times the square root of m divided by k. And so what that means, if you want the biggest period, you want the biggest factor of m divided by k. And so here we see that case 1, we just get m divided by k. In case 2, we get m divided by 2k, so that's smaller than a. So that means b is not going to be the biggest. Case C, we get 4m divided by 4k, so that's the same thing as m divided by k. So in other words, it will oscillate with the same period as case A. And then in case D, we end up with 2m divided by k. That is, in fact, going to be the biggest factor of m divided by k, which means we are going to get the biggest period for case D here. So I would go ahead and pick D, case D. All right, so now let's think a little bit about the oscillation of a mass on a spring and energy conservation. So we've actually already done this. This is old stuff. This is an old slide. We just have a new way of thinking about it. So first of all, let's imagine that we have our horizontal mass spring system, and we've stretched our mass out to some displacement A from equilibrium. So that's the maximum amplitude of the oscillation. Okay, then we know that the total energy has to be equal to the energy at that point in time. If it's at rest, that means that there's no initial kinetic energy. So our total energy is just going to be the potential energy at that point in time. And the potential energy due to a spring is 1/2 Ka squared. And so that tells me that my total energy is going to be 1/2 Ka squared. All right, and so this is going to be fixed at all times throughout the spring's oscillation. So at every single time point in which the spring is oscillating up and down, it will always have total energy equal to 1/2 Ka squared, that initial value. So that whatever the initial value is, it's constant all the time. So it's always equal to that initial value. Okay, and so then in the bottom here, I have a plot of the potential energy. The spring potential energy is a function of x position, so displacement from equilibrium. And you can see that the maximum value, the maximum total value of energy is given by this blue line here. It's a horizontal line at 1/2 Ka squared. All right, then because we know total mechanical energy is conserved, the sum of kinetic and potential energies at any time have to always be equal to that total value, 1/2 Ka squared. So at any point in time, the sum of kinetic plus potential has to be equal to 1/2 Ka squared. And so what that means is that since u is measured from the x-axis up to the black curve, k is just the value from the blue line down to the black curve. So it's the difference between E naught and U. Okay, but it's nice to be able to read it off the graph. So then we want to know what's the maximum value of kinetic energy. Well, the maximum value of kinetic energy would occur when we have no potential energy, right? Since the total is equal to the kinetic plus the potential. If potential is 0, that gives us the maximum kinetic. And so when is the potential 0? That's right at this point x equals 0. So right as the spring is passing through its equilibrium position. So remember, that was when we said that velocity was maximum, right? And so this really corresponds to that as well, since kinetic energy is 1/2 mv squared. So there's a few different ways to think about it. All right, what about maximum potential energy? Well, that's going to occur when the kinetic energy is equal to 0. So that happens right when the total energy is equal to the potential energy. So in other words, there's no kinetic energy. So if you look at our plot here, that occurs right at x equals minus a and a. So those were the turning points of our motion. Remember, that was when we said that the block was at rest, right? So it was going from a positive to a negative velocity or a negative to a positive velocity. And so it had to come to rest right at those end points, right? So either at position x equals a or x equals minus a. And so it's all interconnected. There's many ways to think about those position versus time, velocity versus time, and acceleration versus time graphs. And hopefully energy conservation gives you another way to think about those graphs in a way that makes sense. So I like thinking about it in terms of energy personally. It helps me connect the different ideas. And so then you know that whenever you have maximum displacement, you're going to have 0 velocity, right? So whenever you go through x equals a or minus a, you're going to have 0 velocity. And that's why we refer to those as the turning points. Your mass on a spring will literally turn around. Okay, so let's do another example here. So in case 1, we have a mass on a spring that's oscillating back and forth. In case 2, the mass is doubled, but the spring is the same and the amplitude of the oscillation is the same as well. And so we want to know in which case is the maximum kinetic energy of the mass on the spring biggest. Okay, so I think the trick to this one is just thinking about what's the total energy, and from there you can think about what's the maximum kinetic energy, because that occurs when the potential is 0, and so the total is just equal to the maximum kinetic energy. So what is that here? The total energy is equal to 1/2 Ka squared, so that's that maximum potential energy. We know that both of them, they're the same spring, and so if it's the same spring, that means that they have the same spring constant K, and then we are also told that they have the same amplitude, and so in other words, capital A is the same for both of the two masses on a spring. And so we get the same mu max, which means that we get the same total energy. All right, and so then our maximum value of kinetic energy occurs when potential is equal to 0, and so the maximum kinetic energy is just equal to the total energy. In both cases, then we would get 1/2 Ka squared for the maximum kinetic energy. And so you get the same kinetic energy for both. I will tell you the speeds of the blocks will not be the same because remember K is equal to 1/2 mv squared. So the one that's lighter is going to be moving faster, right? It's going to have a bigger v squared to make sure that it has the same kinetic energy. All right, so I would pick C, they're the same. Okay then, so to wrap up for today, we're going to go ahead and talk about the simple pendulum. So we've basically kind of wrapped up our discussion of the mass on a spring, and now we're going to talk about that second type of restoring force, which is the restoring force that causes the oscillation of a pendulum. So what is a simple pendulum? It's just a point mass, so in other words, it's an object that has all of its mass concentrated in a small spot in space. And so you can think of like, a small bob, a small mass, maybe a spherical mass on the end of a weightless string. So that's what makes it a simple pendulum. It's that all of the mass is concentrated in the little bob at the bottom, and the string itself is considered to be massless. All right. So then when we have this simple pendulum, in equilibrium, the pendulum is just going to hang straight downward at rest. So it's just right at rest. The string is going to be vertical. You're going to have the weight of the bob downwards and the tension in the string pulling upwards to maintain that equilibrium position. Okay, and so then what if we disturb our pendulum from equilibrium? So we pull it to the side. Here I have shown an example where I've pulled it to the right, and so it's moved to the right by some displacement x in the x direction, or you can think about the displacement in terms of the angular displacement from equilibrium, which I'm calling theta. All right, and so then we want to think about what is the restoring force in this case. So really, since our object has been displaced from equilibrium by this amount x, the restoring force is just the force that acts in the x direction to pull our bob back towards its equilibrium position. So in other words, it's really just the net force acting in the x direction on the bob, so on the pendulum, the little ball at the bottom of the pendulum. Okay, so we just have to think about what is the net force acting in the x direction on our pendulum bob, and then we'll be good to go. So to do that, we have to draw a free body diagram. We still have the same two forces acting that we talked about in equilibrium, but now the weight is pulling downwards like before, but the tension will be pulling along the direction of the string. And so since our string has been displaced from equilibrium by this amount theta, then the angle that the tension will make with respect to the vertical is also going to be that angle theta. And so what that means is that the x component of the tension is going to be the opposite, right? So that means it's going to be related to sine of theta. Specifically, it's going to be t times sine of theta. And the y component of the tension is adjacent to that angle theta, so it will be related to cosine theta, right? It'll be t cosine theta. So then we're pretty much ready to go. So let's first think about the net force acting in the y direction. We can use that to calculate the magnitude of the tension in the string. So here the net force acting in the y direction should be 0. It's not moving in the y direction. It's not accelerating in the y direction. And so then we know that that's going to be the sum of the forces acting in the y direction. So here we have the y component of tension up minus mg down. So ty we said was t cosine theta. So rearranging, we get t cosine of theta is equal to mg. And then we use the approximation. So up in the box in the top corner, I have this approximation that for small angles, so theta less than 10, sometimes 15 degrees, we know that the sine of theta is approximately equal to theta in radians, and cosine of theta is approximately equal to 1. So you can go ahead and try it in your calculator. Make sure you switch your calculator to radians, and then try sine of some small angle in terms of radians. And you should get that the sine of the angle you choose is approximately equal to the angle. You can also try cosine of that small angle, and you should get something that's very, very close to 1. Okay, and so then we use that approximation down here. We say that cosine of theta is approximately 1, and so we get T, the tension, is approximately equal to mg. So it's almost equal to the weight of the bob. All right, and then the restoring force, remember, is just the net force acting in the x direction. And so here, that net force acting in the x direction, it's just tension. That's the only force acting in the x direction. And so the x component of the tension we said was t sine of theta. And so our restoring force is really going to be t sine of theta. Here we can also use that nice approximation that sine of theta is approximately equal to theta when theta is in radians, so you'll have to be careful there. And so then we could say that the restoring force is really equal to mg times theta. Okay, I'm going to wrap it up there for today, and I will see you guys in class.